Okay, so for the next sample problem, says here determine the specific volume of nitrogen gas at 10 megapascals and 150 Kelvin based on letter A, the ideal gas equation, letter B, the generalized compressibility chart, letter C, compare these results with the experimental value of 0.02388 cubic meter per kg, and determine the error involved in each case. Okay, so first is we'll use the ideal gas equation only, and then letter B is we'll incorporate the compressibility factor and compare the value from this letter A and from this letter B to these experimental values, so from the table values that's already given to us. Okay, so for the solution, then maybe we can go straight to the computations. So when using ideal gas equation, so we have our form would be the specific volume form. So PV is equal to RT. So V is equal to RT all over P, and we have to find R. So R is equal to nitrogen gas. So from our table we can use this again. Nitrogen gas is 0.2968. so 0.2968 that's in kilojoules per kilogram Kelvin, and the temperature is 150 K divided by the pressure of 10 megapascals. We have to convert this to kilopascals because this one is in kilojoules, so we have to convert this to kilopascals. That is 10,000 kPa. So 0.2968 times 150 divided by 10,000. We have 4.45 times 10 to the negative 3, or 0.004 0.00445 cubic meter per kg. Okay, next is using compressibility chart. We need the reduced pressure and the reduced temperature. So PR is equal to P all over the critical, and then TR is equal to T all over the critical. So given P is 10,000 megapascals, 10,000 kPa. The temperature is 150. So kPa, this is 150 Kelvin. Okay, so now let's go back to the tables and find the critical temperature and pressure. So for nitrogen gas, temperature critical is 126.2. 126.2. The critical pressure is 3.39 MPa. 3.39. Okay, so now let's compute. Then divided by 10 divided by 3.39. This is 2.95. So 2.95, and next is 150 divided by 126.2. This is 1.19. 1.19, or you can say maybe 1.2, and this one is anyway, we'll check the chart. So now going to the chart, so PR is 2.95. So 2.95, you can't use the chart number 1 because the range is only up to 1.0. So we'll be using this chart number 2. Okay, so 2.95. So this is 2.5, then this is 2.6, right? So this is 2.5, and 2.6 is here, 2.7 is here, 8, 9, and here's the 2.95. And the temperature is 1.2. So 1.2. Here's 1.1, 1.15, 1.2. Right, so here is 1.2. Then the value is it's 5, 6, so 0.51. So let's say 0.5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5. So let's say 0.55. So from chart, okay, so from chart, Z is equal to 0.55. So therefore our volume, that is 0.00, let's copy this, times 0.55, right? Because from the equation, PV is equal to ZRT. So we just have to multiply this. So 0.55, 0.00445 times 0.55. We have 2.44, or 0.002447 cubic meter per kilogram. Okay, so now let's compare. So 3, comparing now. So the percent error is, okay, the percent error is equal to, I think the value, let's check this. When using ideal gas equation, this value, the actual value or computed value minus the table values. So 0. 0.00445 minus the table values of 0. Right, minus this all over this. Then let's check if times 100, and let's see the error. So 0.00445 minus times 100, we have 86.34. So we have 86.34% of error. Then when using the compressibility value, so percent error is equal to 0. So this one, okay, minus again this all over table values times, so times 100. Okay, so 0.00247 minus point. We have 2 point. So let me check again. 0. .47. Okay, anyway, 2.47%. So anyway, we can see here the difference. So if we don't include the compressibility factor, then we have this much error. But if we use the compressibility factor, it reduces to this significant. I mean, there's a significant reduction, so 2.47% only. Okay, so I think that's all for this topic about ideal gas equations. So in the next video, we'll be starting the next topic about specific heats. So see you in the next video.